We've been looking at different types of random space and random time functions. Random time functions or time series functions in discrete time, using time series modeling, and continuous space, continuously valued random functions in space, using geostatistics. Now we go one step further. Suppose that you have some model and the input or the parameter of that model is uncertain and described by a random function. The idea is then, okay, what are the random properties, the statistical properties of the output? And this is called forward stochastic modeling. Forward as opposed to inverse, where you try to estimate the parameters from observations. Yeah? So forward stochastic modeling is about having a random input and trying to reconstruct the statistics of the random output. For instance, you have where you measure the water height, and water height is measured subject to some error that will result in an error in the calculated discharge. And obviously you want to know what the mean and the standard deviation, or maybe the probability distribution of discharge is, given that you know the probabilistic properties of the error that you make in measuring the water height. Another one, of course, is groundwater head from unknown conductivity or partly known conductivity. You may only have measured conductivity at a few well locations, but you do not know the complete conductivity field. So what then are the statistical properties that describe our uncertainty about the groundwater head that is being calculated? Another example that we will see today in this lecture is the concentration of a lake that is subject to some input from, say, some nutrients from the agricultural grounds around it, but also these nutrients decay in the water. And if this decay rate is random, what then is the concentration? What's the expected concentration, and what's the uncertainty about that concentration as a function of time? All of these are stochastic forward modeling exercises. And if you put it more generic, let's get the laser pointer out. You have some random function or variable y, which is a function of some random variable or random function as input. Yeah. And depending on, so given, for instance, the probability distribution, if this is a random variable, given the probability distribution of z, or its moments, it may well be that we only know the mean and the variance of z, for instance. What is the probability distribution of y, or the mean and the variance of y? Yeah. Now this can also be extended to from random variables to random functions. So z can also be a random function, and that makes that y is a random function as well. Now, which method to use depends on the form of g. What does the function look like? And what is known about z? Do we completely know the complete probability density function of z, or its multivariate probability density function, or do we only know a few moments, the mean or the variance, or if it's a random function, the spatial or temporal covariance function? Now, in the syllabus, in the lecture notes, these are the classes that are treated. So we have explicit functions and implicit, and of one random variable, multiple random variable, vector functions, explicit functions of random functions of time, space or space-time, differential equations with a random parameter, and stochastic differential equations. And today we're going to look only at these four. The other, how to treat the other cases can be seen in the syllabus, in the lecture notes. Now, one thing I have to explain first is that we are talking about explicit and implicit functions here. And what do I mean with that? Well, explicit means that there's a so-called closed form expression between y and z. So if I know z, I can calculate what y is. Yeah. But if I have an implicit function, then you see that the output is on both sides of the equation. So I either have to iterate to get y, or that's also the case in case of a in case of a differential equation, of course. Then you don't have an explicit, if it's not solved, you don't have an explicit relationship between y and z. Yeah, it's on both sides of the equation. So that's what I mean. Okay. Now we'll first start with a very basic insight from probability calculus. And that's called the derived distribution approach. If this can be applied if we have an explicit function of one random variable. So y is some function of z. Yeah. And if we know the complete probability density function of z, yeah, that's known, then under certain circumstances we can actually derive directly what the probability density function of y is. And that can only happen if the function is monotonous. It means it only increases or only decreases. So there's a one-to-one, there's only one z belonging to one y, and vice versa. It's differentiable, so it is smooth everywhere, and it can be inverted. It means that we can also write z as a function of y, the other way around. Yeah? So under these conditions, we can derive the probability density function of y. To explain it a little bit more in less abstract terms, to look at some graphics. So this is y here, this is z, yeah? So you can see this is a monotonous function because it's only increasing. Of course, the increase, so z, the relationship between z and y, so is only increasing, yeah, or decreasing. If z increases, yeah, y increases as well, as you can see. Or decreases, sorry. If z, in this case, it's a continuously decreasing one. And so not only do we have for every z a unique value of y, yeah, but also the other way around. If we have a given value of y, we have a unique value of z. That's important because it makes that, while applying the function doesn't impact the rank order of the values. Yeah. So if z1 is smaller than z2, then yz1, or the y belonging to z1, is also smaller than the y belonging to z2, right? So there's no change in rank order by applying this function. And if that's the case, if we know the probability density function of z, we can actually derive from this one-to-one what the probability density, analytically at least, we can derive the probability density of y. Yeah. So how is that done? Going back to this one. Well, I'm just giving you the relationships. They are from elementary probability theory. You can derive them easily. But if you can invert the function, y was a function of z, and this is the inverse. So this is z as a function of y. Yeah. We can use the cumulative probability distribution of z, insert the inverted value, and get directly the cumulative probability of y. Yeah, and that's possible because the rank order is not changed by applying the function of y. Yeah? We can do the same for the probability density. Yeah. So we just plug in the original probability density of z. We plug in the inverse, writing z as a function of y. But we have to multiply times the absolute value of the derivative of the inverted function. the derivative with respect to y. And why is that? Well, this makes sure that if we integrate this resulting thing, you end up with a number that's equal to 1, because we have to make sure that the area underneath the probability density function is equal to 1. So this is a scaling factor that makes sure that also the probability density function of y is such that its area underneath it is equal to 1. Okay, let's try to do this for a very simple equation that we all know. So what is shown here is a flow over a sharp crested wire and also a complete or broad crested wire. You can actually, if you've done hydraulics or hydrodynamics course, especially for this case, you can actually derive a unique relationship, because here we have supercritical flow. So any disturbances downstream don't impact upstream water level. So there's a one-to-one relationship between water level and discharge. Yeah? And the form of that is usually a power function. Yeah? Q is A times H to the power of B. Now for a broadcasted wire, we can actually derive theoretically what A and B should be, but in reality A and B are usually calibrated in the lab. Now if you apply this in the field, obviously you install this such a wire, you have to measure the water height. And usually you have some error in there because the water is going up and down, it's bopping up and down, and even though you use what is called a stilling well, which is sort of a connection between a tube well and the open water that dampens the water fluctuations, you can still make an error. And what you want to know is, what if we know what the probability distribution is, or probability density function of H, what is the probability density function of Q? Okay? Now let's do that. So let's go out of this. So I'm gonna try to derive this thing here. So first thing we need to know, this is the function that we have. I'm now using small lettering because basically we're using capitals here because these are stochastic variables, right, or random variables, and now we are just doing it deterministically first. So we have A, H to the power of B. Yeah, this is. So now we're going to invert this one. Yeah, we're going to write H as a function of Q. Yeah, so that's, so this is a G function. So we want to have this one, right? So we're taking, we're just saying, okay, Q divided by A is equal to H to the power of B. Yeah. And then what we can do is we can do both sides. Raise both sides to the power of 1 over B. Yeah. And we end up with H is equal to Q over A 1 over B. Yeah. So we already have then that the cumulative probability distribution of Q is the cumulative probability distribution of H, where we plug in Q over A to the power of 1 over B. Okay, so that's easy. Now we need to do the same for the probability density function, but then we need the derivative of this guy, right? So we need to have the okay. So we take the derivative of this one, yeah? So using the chain rule, that is 1 over B times Q over A times 1 over B minus 1, and then multiplied, because the chain rule, what is inside the brackets, the derivative of that, and that's 1 over A. Yeah. So we go a little bit further there. We can actually simplify that one to 1 over B. Take the A between brackets, yeah, we end up with something like Q, well, this is equal to 1 divided 1 over B minus B over B, so that's 1 minus B over B, right? And of course we got A to the power of 1 over B minus 1, but multiplied times A, so that's A to the power of 1 over B. So that's that thing, yeah. So now we get, now we have the derivative. So now we write the probability density function. So that's the absolute value of the derivative of this one. Well, this thing is strictly positive anyway, so we don't have to do anything about this because A and B are positive. So this is 1 over B. So just make this big thing here. Q to the power of 1 minus B. Is a little bit lack of response, but anyway. And then multiplied times the probability density of H that we know, but we fill in the inverse, right? Sorry. Q over A to the power of 1 over B. So I've derived this for you, and now I also put it a little bit more nicely on the slide, so you can see that actually you can derive theoretically exactly what the probability density function of Q should be once we know the probability density function of H. Yeah, it's quite a powerful method, but it only works with strictly with monotonous, invertible, and differentiable functions. Okay. Let's move on. So if you want to play around a little bit with this where formula, there is this R script called stoch qh.r, and you have to run it once, and then in the console you just type in this function qh, and then you get this, and you can play around with the A and the B and the H a little bit to see what the effect is. This is just a deterministic one. You can also do some other analysis with it, as I show you later. Okay, now it may be that you have a function that is not invertible, for instance, or you don't know exactly the complete probability density function, and that's more common than anything, because usually, if for instance for the water height, we do not have a complete probability density function of the uncertainty about the observation height, but we may know by some replicate measurements in a short time what the average water height is and what the standard deviation of the water height is, or the variance. Yeah, so we only have the moments of Z in this case. Yeah, And if that's the case, then we can use another, it's called the Taylor approximation, which is also quite powerful. The only thing is the variance of Z should not be too large. So if you have a mildly uncertain input variable, in this case Z, and the variance of Z is not too large, and also the function G has to be differentiable, so it has to be smooth everywhere, it has to have a derivative, but it doesn't have to be invertible or monotonous. So it can be also, for instance, a quadratic function, for instance, or a polynomial to the order of 3. That doesn't matter. So it doesn't have to be invertible. And anyway, only has to be differentiable. And it doesn't have to be, sorry, it doesn't have to be monotonous. So in this case, we can compute the moments of y, the mean and the variance of y, if we know the mean and the variance of z. Okay? So let's see how that works. So this is a so-called Taylor approximation of y, or the function gz. So g is generally a nonlinear function of z. And if g is a nonlinear function of z, we can develop it around the mean value of z. Yeah? How do we do that? Well, it's equal to the plugging in the mean of z, which we know, yeah, and then taking the derivative of g with respect to z. This is why it should be differentiable, and then evaluating this derivative at the mean, the value of the mean, multiplying times z minus the mean, yeah, because it's a Taylor approximation with respect to the mean. Then taking the second order derivative, multiplying times z minus the mean squared. The third order derivative, multiplying times z minus mean to the power of 3, etc. Yeah. So this is a Taylor approximation. And what I'm going to show you, that we can actually calculate or approximate using this approximation of the function g of z. We can approximate the mean and the y and the variance of y, retaining one or two or three of these terms. Yeah. And this is this is more seen graphically. This is z, and we know not the complete probability distribution of z, but we only know its mean and its variance. Yeah. And this is g, the function g evaluated at the mean value of z. And this is, and what we want to know, we want to calculate the mean of y, yeah, and its variance. And as you can see, this is the real function. A first order approximation, we only take the first two terms. So this term plus this is a first order Taylor approximation. A third order, we take the first three terms. So we also take, it's called the second order because we take the second order term as well. And the third order, we also include this one. And if you start adding orders, obviously, you're going to be more exact, yeah, as you can see. You can try this also with the where formula, yeah. See how the form of the function is better represented if you add different order terms. So let us derive then the mean and the variance for the Taylor approximation, and we start with the first order Taylor approximation. Yeah. So I'm gonna go out of this again, and I'm gonna go to we start with the first order Taylor approximation, which means that we retain these terms only. Yeah, this is the first order. Okay, so let's do that. So the first order, we first calculate the mean of y, yeah, which is the expected value of GZ, yeah, which is approximated at first order by taking the expected value of this one, yeah. So that's the, oh my god, oh sorry, which is the expected value of G evaluated at the mean plus the expected value of this guy here, yeah. Well, if we inspect this one, we can see the expected value of this term. This is a constant, yeah. So this can be taken out of the expected value operator. So we end up with the expected value of this guy. So we end up with multiplied times the expected value of Z minus mu Z. Yeah? Well, this is just a constant, so this is G mu Z. Yeah? Sorry about this terrible mu. Yeah? But what about this? Well, this is the expected value of Z minus mu Z, which is the expected value of Z is mu Z, so this thing is equal to 0. So this is what it is. This is the first order Taylor approximation of the mean. It's just plugging in the mean in the original function. Yeah? And then the variance, the first order approximation of the variance, yeah, is the expected value of y minus mu y squared. So what is this? This is so if we look at this term, the first two term, yeah, and we subtract the mean, then we get rid of this one. So we only end up with this term. So we end up with, and this is, so we end up with the expected value of is mu Z squared, yeah, times sorry. Oops. Evaluated at mu Z, yeah? And that thing squared times this is what we end up with, yeah? Now this case, this is a constant, we can take it out. And this, we end up with the expected value of z minus mu z squared. What is that? That's the variance of z. Yeah? So we end up with the following approximation. The derivative of g with respect to z evaluated at the mean squared times the variance of z squared. Yeah? So the first order approximation is quite simple. Yeah? The mean of the first order approximation, yeah, is simply plugging in the mean into the nonlinear function, and the variance is equal to the derivative of g with z evaluated at mu z squared times the variance of z. So that's a very simple approximation of the mean and the variance of y. Okay? Going now to the second order. If we go to the second order, what we do in the second order approximation, we're retaining these three terms, yeah, because we're only retaining the second order terms. Now what I'm going to do is I'm only going to do the mean, so this is the second order. Approximation. So in this case, the mean of y, yeah, is approximately equal. Now let's see. We take the expected value of the first three terms, yeah. 1 plus 2 plus 3, yeah. Now if we do that, yeah, well, the expected value of this thing is equal to the mean, to the thing itself, because it's a constant, yeah, it's the function g evaluated at mu is equal to z. The expected value of the second one, we already saw that this thing is 0, because this thing goes out of the expected value, and this is the expected value of z minus mu, so that's also 0, yeah. So we end up with the expected value of this thing, yeah. What is the expected value of 3? Yeah. So this is 1, this is 2, and this is 3. Well, let's analyze that. This thing here, if you have the variance of something, if you take the expected value of something, yeah, that something can go out of the expected value, because this is a deterministic thing. So that is equal to, so the expected value of 3 is equal to half times the second order derivative. So that's 2 differentiating g twice with respect to z, evaluated at mu z, yeah, times the expected value of z minus its mean squared. Well, this thing is nothing more than the variance, yeah, of z. So we end up with that the second order approximation of the mean of y is equal to evaluating the function at mu z plus, and then a half times the second order derivative evaluated at z is equal to the mean multiplied times the variance of z squared. Okay? So this is the second order derivative of the mean. Of course, I could also derive the second order derivative, so this is the second order approximation, Taylor approximation of the mean. I could also have the second order Taylor approximation of the variance, but I refer to the syllabus because it's actually quite big already. If I summarize the result here, we see that the first order Taylor approximation of the mean and the variance is equal to just plugging in the deterministic value, and the variance is equal to the derivative squared times the variance of z. And the second order Taylor approximation is equal to the mean plus a half times the second order derivative with respect to z times the variance of z. And what you can see here actually is that what this shows you that if you what I actually said in the first lecture, that if you have an uncertain input and the function is nonlinear, that the estimate of the mean of the mean of the output is not necessarily the same as plugging in the mean into the nonlinear function, the mean of the input. So we have an additional correction term, as you can see here, which is second order, that shows you that just if you have an uncertain input and you have a nonlinear function, you're never going to get a biased estimate of the mean. It's going to be unbiased estimate of the mean. It's going to be biased. And this is a bias correction, as you can see. Yeah? So if we apply this to our discharge formula, and I'm not going to do that now, I'm going to go through this quickly. First, we're going to get the first and second order derivatives, which we need in the first, first order approximation of the variance and the second order approximation of the mean. So this is h to the power of b. So if we take the first order derivative, we get ab h to the power of b minus 1. Yeah? And then evaluated that h is equal to the mean, so we get this guy here. Yeah? If we then take a further derivative of this, we get a times b minus 1 h to the power of b minus 2. Yeah? Again, evaluated that h is mu h, and this is the second order derivative. Now using these and using these equations, these are our first order Taylor approximation of our where formula. This is the first order Taylor approximation of the mean, and this is the first order Taylor approximation of the variance, and this is the second order Taylor approximation of the mean, as you can see. So there's an additional correction term here, and since the variance of h is positive, a and b depending on the value of b, as you can see, but b is usually larger than 1, you can actually see that if we have an uncertain, if we are uncertain about our water height, and we don't take account of that uncertainty, we underestimate the discharge, and on average, as you can see, because we are neglecting this additional term. Yeah? So you get a biased estimate of the discharge. So this shows you convincingly, I guess, that you always have to take account of uncertainty. You should not be some ostrich sticking your head in the sand as if there's no uncertainty at all. Because if it's there, you should account for it. Otherwise, you get a biased estimate of your discharge in this case. Okay. So before the break, I still want to go to a I call this stochastic forward modeling for dummies, because it's the easiest way to do. If you don't like this analytical stuff, you can go to Monte Carlo simulation. You might ask, why doesn't everybody do this? Well, these analytical techniques were developed in an age, in the 1970s and the 1980s, where these Monte Carlo simulation techniques were not easy, because there were not many computers that you could use to do it on. It was a lot of hassle. These days it's easy. The goal is to get the probability density function or its moments of y. Yeah. And the only requirement is that you know the probability density of z. Yeah. There's no requirements on what the form of this probability should be. Can be any form. Yeah. And also the function can be any form. So it can be even non-differentiable, it can be non-monotonous, non-invertible, can have any, can be a very, can even be a fractal function if you want to, and you could still use this. You could still use Monte Carlo. Yeah. So in this case, any function will do, and it's a very simple procedure. If this is the known probability density function of z, or this is actually the cumulative probability distribution function, which is the integral of the probability density function. We use that preferably, and we basically generate a couple of thousand random numbers between 0 and 1, and from a uniform distribution. Yeah? So a random function, a random number between 0 and 1. Suppose, and then these are actually quantiles that you simulate, and then you can get the associated value of z. So you repeat this 1,000 times. Then you have 1,000 different values of z that are all equally likely realizations of this random variable z. You all plug them into the function, so you get also 1,000 outcomes, and then you just use these to directly estimate the cumulative probability distribution by ranking them from small to large and plotting the rank divided by n+1 against the value. And that's it. It's a very simple procedure. Yeah. So for instance, if you want to do this in R, we have some heavily nonlinear function. You can see it's non-monotonous. It has a very weird form. And then you have, for instance, we assume a Gaussian density. We can generate using R. So we first define the function. This is the function, cosine of z times the exponential of z squared divided by 40. That's this function here. And we generate 1,000 realizations of a random deviate with a mean 2 and a standard deviation of 0.5. We plug these z and we get directly y, and this is a plot of the histogram of z, and this is a plot of the histogram of y. It's very fast, it's very simple to do. Now you can play around with this stochastic, you can play around with this guy here, generating uncertain values of h and getting uncertain values of q, yeah, as you can see. So, well, I can actually do that. So here you can see this function. This is basically this R script gives you a lot of different functions. So they're not calling the functions here, but are only defining them. So you run it to define the function, and then you can maybe get stoch qh.r out by qa stoch 1. So we just evaluate QH, what is it? Stoch 1. And there we have it. And we can, this is the mean of H. We change the mean, then we get a higher Q, as you can see, obviously. We can also increase the variance, so we are more uncertain about the actual water height, and this gives us the distribution of Q. Yeah? Of course, that depends also on the value of B, how that turns out. Yeah? So you can play around with this guy here. Yeah? Okay. So what I've done here, and then we're going to have a break. What I've shown here is how effective Monte Carlo simulation can be, and how easy, because here we use the where formula. So what I've done here is I calculated the theoretical cumulative probability distribution function using the exact derivation, the derived distribution approach, with assuming that H follows a Gaussian distribution with a mean of 0.3 and a standard deviation of 0.02. Yeah, so we can see the probability distribution, the cumulative probability density function of the discharge Q. Yeah, and so the straight line is that, well, this is equation 8.2 from the syllabus, but that's the exact derived distribution. So this is the exact solution. And we also run 1,000 realizations of H with exactly this mean and this standard deviation, plug them into this formula, and then computed the cumulative probability distribution experimentally by plotting the rank divided by the number, by 1001. That's the number of observations plus 1 against the value, and we see it exactly reproduces what we see from the what it theoretically should be. So it's quite effective. Yeah. What I've done here is computing Monte Carlo simulation, which is actually the close to exact solution with the approximate solution from the Taylor approximation. Yeah. And what I've done here is I use these parameters A and B, and H is again Gaussian with a mean of 0.8, but I'm increasing the standard deviation of H, yeah, from even very uncertain to 0.3 meters. Yeah, if you are in a big river, for instance, you can have these huge errors in the water height. And what is seen is that this is the exact one. So there's a function of the discharge as a function of the standard deviation. You can see actually that the discharge increases if the standard deviation increases, and that is because if B is larger than 1, yeah, then larger excursions of H have a bigger impact of Q than smaller excursions from H, yeah, because of the value of B being larger than 1. Yeah, and you can see that the first order Taylor approximation, you see a bias in the estimate of the discharge. So if we just ignore the uncertainty and we use a first order approximation of the mean, we see that we're not doing very well. A second order approximation, however, is doing much better. Yeah, it at least get the right tendency. It overestimates a little bit, but it gets the tendency right. And what you can see is how effectively actually the second order or even the first order Taylor approximation of the variance already is compared to the second order. So what I usually use if I want to do an approximation is use a second order approximation of the mean, and because of its simplicity, a first order approximation of the variance to get a quite realistic approximation of the mean and the standard deviation of the output. So with that, it's the end of the first part of this lecture.